Okay, so last section we're going to look at is 11.2, and it builds off 11.1 because in 11.2 we're going to look at sequences again, but we're not just going to look at a sequence by itself. We're going to look at what happens when we add up all the numbers in a sequence, and that's called a series. And just like when we work with sequences, if you want to predict what the 50th term would be, you really want an explicit formula to do that. So same idea with a series. If I said to you, add up the first 50 terms in the sequence, you don't want to have to do that by hand. Okay? You want a way that you could find the sum of the first 10 terms very quickly, first 50, first 1,000, anything you wanted, without doing it by hand. So we're going to try to come up with formulas for adding the numbers up in a sequence, okay? Just like we came up with formulas for sequences. All right, so in yesterday's section, that's the notation we use to represent a term in a sequence. A sub 1 would be first term. A sub 12 would be the 12th term. So here's a sequence that describes the nth term. So let n be any number you want, but because it's terms in a sequence, n is restricted to being what kind of number? Positive, and what else? It can't be a, well, positive means it can't be 0, but it has to be a whole number. Yeah, can't be fractions or decimals, because if n was 1.3, there's no such thing as the 1.3rd term. There's a first term, there's a second term. There's nothing in between. Okay, so n is always a positive integer, or a counting number, you could say it that way. All right, so now using that sequence, what I'm going to do is I'm going to generate some terms, and I'm going to add them up. If you plug in 1 for n, what's 2 times 1?
1.
2. Minus 1? 1. And then if you square it? 1. So if you add up the first 1 terms in that sequence, you get a 1. So if you add up just that first term, that's all it is. There's nothing to really add up. So this notation, S sub 1, that's going to mean the sum of the first n terms. So S sub 1 just means the sum of the first 1 terms. So there's nothing to really add up. Okay, S sub 2 is going to represent the sum of the first 2 terms in that sequence. So we already know the first term is a 1. Let's look at the second term. 2 times 2? Minus 1? And then 3 squared would be 9. Or we could just leave it as 3 squared for now. So S sub 2 would come out to 10. So that's 1, that's 10. S sub 2 is the sum of the first 2 terms in that sequence. Okay, let's do one more. S sub 3. Now you're going to add up the first 3 terms. Okay, so we already got the first term, we got the second term, we didn't get the third term yet. What's 2 times 3? 6 minus 1, and then we're squaring it. Yeah. So the sum of the first 3 terms would be 35. And then in general, if you wanted to write out the sum of the first n terms, it would be the first term plus the second term plus the third plus the fourth plus all the way up to the nth term.
Wouldn't that take like a really long time if we're going to do 50? Right?
If you were going to do 50, yeah, you'd, by hand, it would take a long time. Okay, but what we're going to try to do is look at this pattern here, 1, 10, 35, and we could find another one. We're going to try to find a pattern in these numbers. And if you can figure out a pattern in those numbers, then you can find any sum that you want very quickly. So does everyone understand the difference between finding a formula that gives you the terms in a sequence and finding a formula that would give you the sum of the terms? This one might be kind of hard to figure out, but any question on the difference between those two formulas? Okay, one would give you the terms, one would give you the sum of the terms. And this is a common one, okay? You're adding up the first n odd numbers squared. That's how you would describe this. So if you wanted to find S sub 10, you would be adding up the first 10 odd numbers squared. 1 squared, 2 squared, 3 squared, all the way up to the 10th odd number. Okay. Any questions on that idea? Okay. So we'll see that notation a lot today, S sub something. Okay, that S sub n, that notation that I was using, that's called a finite series. Because n is going to be a number. Like Luke said, it could be 50, it could be 100, it could be 1,000,000, but it's not infinity. Okay? It has an end. So how many numbers are you adding up? You're adding up the first n. Finite means you stop. Okay? There's a certain number of terms that you add, and then you're done. Again, that number of terms could be huge, could be billions, but there's still an end to it somewhere. Okay, so finite just means not infinite. It's not forever. And series, I mentioned this earlier a little bit, but series just means addition. So finite series means you're adding a certain number of terms together. That's all a series is. You're adding terms in a sequence together. All right, so if we had a sequence A sub n, sometimes we use B sub n, whatever you want. You can name the sequence using any letter. If we made a new sequence out of that was the sums, okay, that's called a sequence of partial sums. And I think it'll be easier if I just go back to the other page for a second. If you wrote down this sequence, 1, 10, 35. What I just wrote right here, that's a sequence of partial sums. 1 is what you get when you add up the first 1 terms. 10 is what you get when you add up the first 2 terms. 35 is what you get when you add up the first 3 terms. So each number in this list that I just wrote represents a summation. And we did the calculations earlier up above. So this is a sequence of numbers where each number in the list is a sum. And that's called a sequence of partial sums. Okay, the first partial sum is always easy to find because it's the sum of the first 1 terms in the sequence. Well, if you're only adding up the first 1 terms, there's nothing to add. So the first partial sum is just the first term in the sequence. The second partial sum is the first term in the sequence plus the second term in the sequence added together. What would the third partial sum be? The first term plus the second term plus the third term. And the reason we call it a partial sum is because maybe this sequence A has 10 terms in it. If you only add up the first 3, you haven't added them all up. You've only added up part of them. So that's why it's called a partial sum. Okay, and then lastly, if you wanted to add up the first n terms, you add up the first one, the second one, the third one, the fourth one, the fifth one, all the way up to the nth term. But it's important to understand that that n is a fixed value. It is not infinity. Maybe it's 100 terms, maybe it's 1,000, maybe it's 1,000,000. but it ends somewhere. Okay. And that one we would call the nth partial sum. Okay, so as I said earlier, we've got to figure out patterns in the summation sequence, because you're not going to be able to add up the first 100 terms of a sequence by hand easily. Okay, it's going to take too long, and if you make one mistake early on, it messes everything up. So there's got to be a way to come up with a formula to do that. Okay? And that's what we're going to figure out. Okay. Anybody still copying? Okay. So first thing we want to come up with is a nicer way to write this stuff down. Okay, we want to have a shorter way, a more compact way to write stuff. Now, this notation I'm about to show you, calculation-wise, doesn't speed anything up. It's just a shorter way to express on paper something plus something plus something plus something plus something plus something, a bunch of additions without having to write it all down. Okay, and it's called sigma notation. Okay, and again, just to be clear, this notation doesn't speed anything up. It's just a short way to write things on paper. That's all it is. So let's say we wanted to represent adding up A1, the first term, plus A2, the second term, plus A3, plus A4, plus A5, plus A6, all the way up to the nth term. And you didn't want to write that down, because maybe n goes to 1,000. You don't want to write A1 plus A2 all the way to 1,000. So there's a very short way we can write it. Has anybody ever seen that symbol before?
Is that Greek?
Yeah, it's a Greek capital letter. It's the Greek. Anybody have a guess what capital letter it is?
EU.
It's sigma. Yeah, sigma. So, and the notation, it has three parts to it. It has something on the bottom, it's got something on the right, and it has something on the top. Yeah, I'm going to explain what those parts are. Okay, so if you want to write down a summation, first thing you need is a sequence that you're going to sum. Okay? This is your sequence. This is the formula that is generating the terms you're going to add together. Okay, so maybe it's something like 2n plus 6. Okay, just making up an example. So they're going to have to give you the sequence. And actually, if I was doing it like this, I would use the letter K. Whatever letter is on the bottom, that's the letter they would use when they write the formula. We've been using N a lot. We might switch to using K a little bit. It doesn't really matter. Okay, so that's the formula that generates the sequence. This basically tells you where you're going to start. What term do you want to start at? You want to start adding, you want to start with the first term? Do you want to start with the second term? Where do you want to start? This tells you where you're going to end. Okay, so on the right-hand side is the formula that generates the numbers you're going to add. The bottom says where would you want to start. The top says where do you want to stop. Okay, so I'm going to show you an example. Does everybody have the top part of sigma? Okay, so in this example, the notation I'm using here is representing adding up the first 5 terms. That's it, just the first 5. How do I know it's the first 5? Well, k is starting at 1, and it's going to end at 5. Okay, so if I wanted to do this out, what I would have to do is plug in every number from 1 to 5. So by every number, I mean 1, 2, 3, 4, 5. Into this formula and calculate each result and then add them up. So if I plugged in 1, what's 2 times 1? 2 plus 3, 5. That's the first term in this sequence. Now I'm going to add it to the second term. How do I know I'm adding? That's what that capital Greek letter means. It means take each result and add. Plug in 2. What's 2 times 2? Plus 3. So there's the second, third, the fourth, and the fifth. Whatever that comes out to, that's the answer to that problem. So as I said, it's not a faster way to do it. It's just a faster way to write it on paper. That's all. So any questions on how to use that notation? Right-hand side is your formula. The bottom is where you start. The top is where you stop. And you'd have to add these up. You'd actually type it in and do this out. Yeah, I think it would be 45 if I did it right. Does anyone know how I did that in my head? I didn't really add those up.
You put the 7, 13, 9, and 11.
Well, the way I thought of it was 9 is right in the middle. And everything is symmetrically spaced around it. I have 2 numbers. I have a number that's 2 lower and a number that's 2 higher. I have a number that's 4 lower and a number that's 4 higher. So really what I could do is think of it as an average. What's the average of 7 and 11? 9. What's the average of 5 and 13? 9. So what I could do is think of these as all 9s, and I have 5 of them. Okay? Taking into account some are lower, some are higher. So I just, in my head, I did 9 times 5 to add that up. Okay? Just kind of a clever trick because it's a nice pattern to figure out the sum. Okay, so when you use this symbol, I think you already wrote this on the other page, but that symbol is called sigma notation. I'm just writing that because I'm going to compare it to doing this. That's called expanded notation. So sigma notation uses the Greek letter. Expanded notation is when you write the whole thing out. If I go back to what we just did, sigma notation, what's in the box is expanded notation. Any question on the difference between the two? So if I give you a problem on the test with a sigma, and I ask you to expand it, that means I want you to do what we just did on the other page. Write out each term and add them up. Okay, so here's another one. They're asking us to expand the sum. Where are they telling us to start? Plugging in k equals 1. And sometimes you can start at 2. I mean, it just depends on where they want you to start. Where do they want you to end? N. So because n's not a number that we know, it would be a finite number. It's not infinity. What I usually do is do the first term, do the second term, do the third term, and then put a dot, 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 and then plug in n as the last one. Okay, because we don't know how many numbers are in between 1 and n. We don't know. Okay, so let's start with 1. Alex, 2 times 1?
2.
Plus 3?
5.
And then squared it. We can just leave it as 5 squared. That's fine. Okay, so we got 5 squared. Let's do the next one, 2. Lauren, what's 2 times 2?
4.
4 plus 3?
6.
7, and squared. Ethan, what's going to be the next number squared? So yeah, 3 is what you're going to plug in, but let's do that out. What's 2 times 3? And then plus 3? 9. So 9 squared. And now, we can kind of see the pattern. 5 squared, 7 squared, 9 squared, 11 squared. Let's go all the way to the nth term. What do you get if you plug n in for k? 2n. Yep. Plus 3 and squared. That's how you expand it. Okay, so I put this dot, dot, dot because I don't know how many more there are. If you can fit all that on the same line, that's good too. But, any questions on expanding that sum?
Is there a formula to add up to a n term?
Yes. Yep, especially when it's a pattern like squared. There is a formula we're going to go through. We're going to go through adding up like a couple different cases. I'm not sure if we do odd numbers squared, but there's definitely a formula for it. Yep. Some of these formulas are kind of hard to figure out, so I'm going to give you a hint with some of them. Okay, but that's going to be the next thing we look at. Okay, before we do that, I want to look at a problem kind of like this. How can you take 2 separate summations and combine them together? And you pretty much do what you would kind of expect. It's like combining like terms. As long as these are the same and those are the same, you're good. You can combine like terms. Okay? And that's basically what I'm showing you right here. If you wanted to do a sum of 2 different sequences, it's exactly the same as adding up all the numbers in the first sequence, adding up all the numbers in the second sequence, and then adding those results together. Okay, for this one, I'll show you an example. And we'll do it the way it is on the left, and then we'll do it the way it is on the right, and you'll get the same thing. Let's say a sub k, and I'm going to make these very short sequences, was the sequence 1, 3, 5. B sub k, different sequence. Let's make it 2, 4, 6. Doing it the way on the left, actually, let's do it like this. Doing it the way on the left says, first add each individual term together, and then add up all the results. So we're going to add what's in AK to what's in B sub k. And we do it term by term. So what's 1 plus 2? 3. The next one in A sub k is 3. The next one in B sub k is 4. What's 3 plus 4? 7. The next one in AK is 5. The next one in BK is 6. Add those up. What's 5 and 6? 11. So what I just did was that part. I just added up each individual term. Now I'm going to do that part. Take everything I just got there and add them up. What's 3 plus 7 plus 11? 21. That's doing it the way on the left. Now let's do it the way on the right. The way on the right says, take all the numbers in AK and add those up first. 1 plus 3 plus 5. What's 1 plus 3? Plus 5? 9. Now it says, take all the numbers in B sub k. Add those up. What's 2 plus 4 plus 6? 12. And now the last step is to do that. Take the 2 results you just got and add them together. What's 9 and 12? 21. You get the same thing. So whether you do it the way on the left or the way on the right, it comes out the same. Okay, so what that basically means is if you're given something like this with 2 separate sigmas, you can basically combine like terms in the two sequences. Okay, so that works with addition. If you didn't want to copy rule 2, you could just change rule 1 to a plus or minus. If you're plussing, you're adding. If you're minusing, you're subtracting. But rule 2 it's the same as rule 1 for subtraction. So actually, I would just put plus or minus. Then you don't have to copy the whole thing. Notice the key too. They all start at the same spot. If one of them was different, okay, this index, that's what we call that number. If it was different, you can't do what I'm showing you. Okay, and the last rule has to do with multiplying a sequence by a number. So what it basically says is if you want to multiply a sequence by a number, you could multiply each term in the sequence by the number first and then add. Or you could do it the other way around. You could add first and then multiply last. And you get the same thing. And this one I'll show you again with the numbers. Let A sub k be the sequence 1, 2, 3. And let C equal 4. If I wanted to do C times A sub k, what that means is take every term and multiply it by C. Okay. So we're going to multiply everything by 4. What's 1 times 4? Now do it 2 times 4. 8. Oops. 3 times 4. 12. So we just did this part. We took the sequence and we multiplied everything by C. Now this part says add them up. So yeah, we get 24. Now, the way on the right, a little different. Add them up first, multiply last. So what do you get if you add 1 plus 2 plus 3? 6. I just did that. Now take that and multiply by the number in front, which is 4. What do you get? 24. Okay. So the point is, if you have a number that is being multiplied by a sequence, you can put that number in front of the sigma, and you get the same answer. Okay, and those are the only rules that we really need. So there's really only 2 rules. If you count the first one, it's the same rule, plus or minus, and then this rule. So let's combine these into a single sum. This is rule 1. Take your 2 sequences, AK and BK, and add the sequences together. We don't have actual terms that we're adding, but we do have some like terms we can combine together. When you write it as a single sequence, it starts at the same spot, it ends at the same spot. What would be my squared term if I combine those 2 sigmas together?
6k squared.
Yep, 6k squared. So we took care of that. How about my k term? Yep, negative 2k. And what about my constant? 3. And that's it. Any questions on combining those into a single summation? You're just combining like terms, yeah. And now there's 2 things here you would have to deal with if you really were going to do this out. You have to know how you add up squared terms and how you add up linear terms. There's patterns for both of those. And that's what somebody asked about earlier. Okay, but that's all we're doing with that for now. We just combine those together. So this is the point that I've been kind of getting at the whole time. In sigma notation, it is a compact way of writing it, but it doesn't speed up anything. if I wanted to add up the first 10 integers, which is what this is, plug in 1, you get 1. Plug in 2, you get 2. Plug in 3, you get 3. Plug in 4, you get 4. You're plugging in every number from 1 to 10, and you're adding them up. You would still have to do that out. Okay, there's got to be a shorter way to do it out. And that's what we have to look for some patterns. So this pattern is relatively easy to find. But the ones after that, they get kind of harder to find. So I'm going to give you what they are. We're never going to add up anything more than things that are squared in this class. Okay? So at most, just up to squaring things. All right, let's take a look at this one. So if we're adding up integers, what do you get if you add up the first 1 integers?
Integer
Which is 1. What if you add up the first 2 integers? I'll just put them over here in case you need to see them. You get 3. What if you add up the first 3 integers? 6. The first 4. And 15. We'll stop there. So the key now, actually, you know what? Let's do one more so I can show you something. 21. The key is to find a pattern in those numbers. And it's not as easy of a pattern to find. But I'm going to show you a trick so you can at least figure out, does the pattern involve squaring? Does it involve cubing? What does the pattern involve? What I'm going to do is I'm going to subtract numbers that are next to each other. What's 3 minus 1? 6 minus 3? 10 minus 6? 6. Now, I want to do this subtraction process until I get a row of numbers that's the same. And then I'm going to stop. What's 3 minus 2? 4 minus 3? So now I've achieved a row of numbers that's the same. How many times did I have to do this process to get to a row of numbers that's the same? Twice. Because I did it twice, this pattern is going to involve squaring. It's going to involve something squared. It doesn't tell you exactly what it is, and that's not really the point of what we're doing. But it does tell me that it's going to involve squaring. And the pattern, this is one of the only patterns that I just remember. It's n times n plus 1 over 2. You might be like, well, wait, that's not squaring. But if you did it out, there's the pattern. Let's try it. These are the term numbers. Let's see if we plug a 4 into that formula, do we get 10? What's 4 squared? 16 plus 4? Divided by 2. 10. Gives me that one. Let's try it for 5. What's 5 squared? 25 plus 5? What's 30 divided by 2? There's that one. So now, if I wanted to know, what would I get if I add up the first 10 integers? And I didn't want to sit there and do 1 plus 2 plus 3 plus 4. I could just plug in 10. 10 squared is 100. 110. What's half of 110? 55. So if you want to add up the first 10 numbers, 1 through 10, the answer is 55. And if I wanted to do the first 1,000, I could do it just as fast. 1,000 squared plus 1,000 divided by 2. Without sitting there and doing it out. Okay. So that's what I'm going to show you now. Some special patterns. I think there's 2 other ones I'll show you. Bless you. The first one is even a step simpler than the one I just did. It's basically doing something like this. You're adding up a constant over and over. It's not even a formula with a variable. So if you did this out, if you plug 1 into what I just circled, what do you get? 6. If you plug in 2, what do you get? into this formula. Plug in 2 for k in that formula. Go, Brett. Remember, it's a constant. So what do you get when you plug 2 into that formula? 6. How about when you plug in 3? 6. How about when you plug in 4? 6. There's no way to plug in anything. It's just the same thing over and over. Plus 6. So you have 6 plus 6 plus 6 plus 6 plus 6. What's a shorter way to say that? 6 times 5. Okay, you're just adding up the same number over and over. 6 times 5. Okay, so if that's all you're doing, you just take the number in front times the number at the top. You're just adding up the same number over and over. The second one is the one I just showed you. This is the formula for adding up the first n integers. So like, if you want to add up the first 5 integers, it'd be 1 plus 2 plus 3 plus 4 plus 5. That's the formula you could use to do it. And the last formula I'm going to show you is the formula for adding up the first n perfect squares. So now you're not adding 1 plus 2 plus 3 plus 4 plus 5. I'm sorry, not perfect squares. The first n integers squared. You're adding 1 squared plus 2 squared plus 3 squared plus 4 squared. That's what this formula does. Which, yeah, that is the first n perfect squares. I said it right the first time. That's fine. And that's a tough one to come up with. You probably you wouldn't really be able to come up with that easily. You could do that pattern that I showed you, that difference tree, and you would see you'd have to do it three times before you got a row of constants. So it would tell you that it's something cubed. Like if you FOILed all this out, it would be a 2n cubed in it somewhere. But it would still be hard to come up with. And you can look up any formula you want. You can look up the formula for adding up the first n numbers that are cubed to the 4th power, to the 5th power, many formulas as you want. But that's as high as we're going to go. All right, so I want to try to simplify that. Okay, sigma notation looks great on paper, doesn't save us any time in calculations. First thing I'm going to do is kind of the reverse of what we did before. I'm going to break this into 2 summations. 1, 2. They're both k equals 1 to n. What's going to be my pattern in the first one? It's going to be my formula. Minus 2k plus, what's going to be the number in the second one? 3. Now, this is something we just did on the other page. You're adding up a constant times n. So you're adding up the number 3 n times. 3 plus 3 plus 3. So we'll come back to simplifying that in a second. What can I do with this negative 2? I said that when you have a number in front of the sequence, you can move it somewhere. Where? Yeah, we can put that in front. And when I do that, watch what happens. I get negative 2 times the sum from k equals 1 to n of k, plus the other part stays the same. you should recognize this. The sum from k equals 1 to n of k. Let's go back. The sum from k equals 1 to n of k. So we can replace what I just circled with a formula. We have the answer to it. What can I replace this with? Yeah, you could FOIL this out. You're going to have to eventually. If you don't want to, you can leave it like that for now. But go ahead, Bria. If you FOIL it out, what do you get?
So we x squared plus n over 2.
Yeah, we just got rid of the sigma. That's the goal. When you're simplifying sigmas, you want to get rid of them. And what about this one? If you add up the number 3 n times, what would you get? 3n. Adding up the same number over and over, that's multiplication. Now, from here, we just have to do out the arithmetic and see what we get. Because we could simplify a little bit. What property do I have to use with the negative 2? Yep, I have to distribute it. Or, actually, even an easier way, think of that as a fraction. 2 in the top here, 2 in the bottom. What happens? They cancel. If you distribute it, that's fine. You just have to cancel it after. What's left on the outside? Outside. Negative. Right? That negative is, the 2 canceled, but the negative is still there. Now, what do I have to do with that negative? Yeah, now I have to distribute. So negative n squared minus n plus 3n. And yeah, now combine like terms. That's the formula. So if you wanted to do this, the way to do it would be to use that formula right there. So if I wanted to add up, say, the first, and I'll do this one, the first 100 terms in that sequence. Okay, the way I would do it, plug in 100. So I get negative 100 squared plus 2 times 100. And I have to do that out. Okay, see what I get. But that's how you could do it. So very, very quick way to add up any number of terms you want. Any questions on what we did there? It's kind of the goal. Look for substitution. And it's always going to be substitution with usually one of these 2 formulas, because those are easier to do. This one's a little harder because there's more foiling you have to do. And I didn't show you the 4th one, so we'll just stop there. I think we need to see another one of those. If I did it, I would probably do it without that term. So 5k minus 2, negative 2k plus 3, it would be almost identical. Except you'd be distributing a 5 instead of what we had before, a negative 2. All right, so I'm going to show you a formula, a special formula for adding up terms in a geometric sequence. And in particular, it's going to be a finite geometric sequence. What does finite mean? It has an end. Anything that has an end, you can add it up. Even if they said to you, add up the first billion terms, that's a lot, but you could do it, or a computer could do it. Okay, it has an end. So the formula, if you want to add up the first n terms in a geometric sequence, is this. You need the first term. That's a sub 1. first term in the sequence. The next thing you need is R. That's actually the last thing you need. Does anybody remember what R was? The common what?
Ratio.
Common ratio. So if you get something like this, what's the common ratio in that sequence? 2. Yep. The common ratio also happens to be the same as the first term. That doesn't always happen. Here's one where the common ratio is 2, but the first term is 3. Okay. So to add it up in a geometric sequence, first n terms, use that formula. How do you know a sequence is geometric? Both of the examples I just gave you are. But what does geometric mean?
You're multiplying.
You're multiplying. You would not use this formula on something like this. That's not a geometric sequence. That's arithmetic. Okay, so I want to find the 12th partial sum. Before I even do it, does anybody notice what's happening to my terms? The first one is 2, then 2/3, then 2/9.
The bottoms being multiplied.
The numbers
It's
are
getting
smaller.
smaller.
What's it being multiplied by each time? The whole fraction.
Third.
1/3, yeah. So the next one would be 2/27. The next one would be even even smaller. So eventually, if you were to continue this out, say, for quite a few terms, this number is getting closer and closer to what? 0. It's never going to reach 0, but it's going to get very small. So let's add up the first 12 terms in this sequence. So S sub 12 equals, take the first term, which is 2, times 1 minus r to the n. So I asked you what you're multiplying by each time because you need to know that. What was the common ratio? 1 minus r to the n. And actually, we're doing 12, so fill in 12 for n. Divided by 1 minus 1/3. Okay, now we just type that in. So 2 times, let's at least do the bottom out. What's 1 minus 1/3? 2/3. And now I'm going to use my calculator to type that in. So we've got, I'm going to do it in a couple steps because there's a lot of parentheses here. 1 minus 1/3 raised to the 12th. Okay, just to make this clear, the 12 is right there. Okay, so 1 minus 1/3 to the 12th. I'm going to divide that by 2/3, and I probably need parentheses around it. And then I'm going to hit times 2. So if you add up the first 12 terms in this sequence, that's what you get. What do you think you would get if you added up the first 20 terms? What do you think's happening here? Maybe a little bit bigger. How about if I added up the first 1,000 terms? What do you think I would get? Pretty close to it. 3. So this is a sequence that if you added up every term to infinity, it would never get bigger than 3. The reason? What you're adding each time is getting smaller and smaller and smaller. So you have 2/9. That's the next term. That's the next one. See how small the terms are getting each time you add one? Eventually it's so small, it's like it doesn't even make a difference anymore. And that's why you could add up every term from 2 to infinity, and it would never go above 3. Okay? The idea of adding things up to infinity, that's what we're going to look at tomorrow. But you can kind of see that a little bit here. If you add up the first 12 terms and it's like 2.9999999, my thought would be it's probably getting close to 3 and it's never going to go above that. And that's exactly what happens here. Okay. So any question on adding up a finite amount of terms in a geometric sequence? If you forgot that formula, what you could always do is you could do this by hand. It would take kind of a while, but you've got the first 3 terms. You'd have to write out 9 more, and then enter each one on the calculator and hit add. It's probably a lot faster to just do it this way, especially if I said add up the first 100 terms. That's going to take too long. Yeah?
Can we go back to the page?
The other page?
According to that formula, yes. Okay, thank you.
Yep. So that's definitely an important formula to know. Okay, so homework it's on 601, and it's just 1 through 19 odd. Okay, 1 through 19 odd. Okay, we'll take a look at that tomorrow, and then tomorrow we'll finish section 11.2, which I think it's actually a little shorter than what we did today, and then that'll be it. Okay, don't forget that I'm after school today for extra help if you need to come before the test. Also, if you have any homework you need to show me, you got about 7 or 8 minutes. Make sure you just come on up and show me that.